Hello, this is Daryl Korn, and this is my walkthrough of Homework 4. We got a lot to talk about, so let's get into it. All right, starting first with the code. Here's my code for my k nearest neighbors regression. We're going to run it real quick while I talk through it. So the k nearest neighbors, we're going over the different metrics, going over different k values here, right there, and then we fit our model, of course. So all of my models here in my code, I've truncated them just to cut down on training time because we don't have a lot of time to present. But in the presentation, they're more fleshed out fully. So we're trying different k values here, all for the Euclidean distance. And after 5, we should be showing a graph like so. Okay. Then here is my naive Bayes classifier. I'll also run that. This one's fairly quick. So here we iterate over different alpha values before we fit our multinomial naive Bayes. We can also pass in different scalars to test it out. And I believe we just test a handful here before we generate our graph. Like that. Yeah. Here is our random forest code. I performed a little grid search because there's so many parameters. I wanted to get a sense of where I should be tuning things. This one takes a bit longer to run, so I'm not going to run it, but this is generally what it outputs right here. That one, I'm testing the different max leaf nodes. Here, this is my gradient boost code. Pretty similar to random forest, really. So testing different n estimators. And then my last notebook here is just kind of testing and comparing all of the different models at their best. So they're different, their best train and test accuracy on the full data, no longer doing cross-fold. Here we're looking at feature importance for naive Bayes. Here's feature importance for random forest, feature importance for gradient boost, and then we look at some misclassified samples. So just looking at what they got wrong, how many in each class, all that fun stuff. Okay, let's look at the results. So for the k nearest neighbors binary classifier, I attempted 3 different scaling techniques. I did no scaling, min-max scaling, and standard scaling. I also looked at 2 different distance metrics, Euclidean and Chebyshev. I didn't look at Manhattan because it was giving the same results as Euclidean, so we just tested these 2 to save time. And I found that the best results were when we used a min-max scalar at Euclidean distance with a 10K parameter. So that gave us a fairly low test accuracy of 65.3%. And we can see from these graphs that the Chebyshev distance, like figure 2.1 here, was way outperformed by the Euclidean in training and test data. It starts, like underfitting like almost immediately in a lot of these cases. And not and we typically see overfitting definitely before k equals 10 for the Euclidean, and that's oh no, skip too far ahead. Also represented in this table in the bottom right here with the different best metrics for all the tests. Okay, on to naive Bayes. So for naive Bayes, I only attempted 2 different scaling techniques, either no scaling or min-max. I could not use the standard scaling because you need to have all positive values for naive Bayes to work. So given that, our best results happened when we did not use a scalar and our alpha was just 0.1, and that gave a much better test accuracy of 83.3%. I decided that none was better than min-max scaling because they actually did give very similar test accuracies, but none had a little bit of regularization to it, so I think it would generalize better. You can see here, we see naive Bayes. It starts to underfit quite rapidly after 10. Okay, on to random forest. And before I get too far into random forest, I wanted to talk about the scaling techniques I used for it. So for decision tree algorithms, it's known that scaling does not have a very big impact on it. And I also found that in my tests. So this is because decision trees have an easier time finding these thresholds between classes when the data is not scaled. So going forward, I'm not going to test min-max or standard scaling on random forest or gradient boost, uh, just to kind of focus the report more and have a smaller set of results to analyze, as well as just to refrain from really long training times because you're testing a ton of different hyperparameters for these algorithms. And these graphs here are just backing up what I've said above. So figures 4.1 to 4.3, that's me testing the max features of random forest on different scaling techniques, and I was just getting the same results each time. Furthermore, in this bottom right graph here, this is me testing the max depth or different values of max depth for random forest. And it looks like there's only two lines, training and validation, but really this is three different scaling techniques just overlaid on top of each other. And the results are so similar that they're just being covered up. So you're really only seeing standard scalar because that was the last test I performed and plotted. So going forward, only using no scaling for random forest and gradient boost. Okay, so for random forest, my best hyperparameters that I found were with no scaling, of course. I used 100 estimators because that was a good balance between power and time to train. For my max features, I found the log base 2 of the features was a good amount. So that was because we had 1,000 features. That was only about 10 features per tree. Max depth of 30, 100 max leaf nodes, and this gave a test accuracy of 82.21%. And this was some of the results of the tests that I had and how I landed on these parameters, I suppose. Okay, on to gradient boosting. So similar as before, no scaling. And this time I found that I only wanted about 100 in estimators because you can start to overfit if you have too many estimators for gradient boost regression tree. So we kept it a little bit lower. Max features, I used 10%, so that is about 100 features. Only a max up of 5, so that we don't overfit there either. And then we have a much smaller 20 leaf nodes, and the learning rate was at 0.15. And this gave, interestingly, a very small R-squared score at 47.84%, but this improves later, as you will see. And we'll show that right here in the model comparison. So once we went from cross-fold validation up to just training on the best parameters for the entire train data set and then testing on that held out test data set, it was clear that k-nearest neighbors perform the worst. So we're not going to discuss it too much. The best performances came from naive Bayes, random forest, and gradient boost, these three. And technically, naive Bayes performs the best on the test, but only by 2/100ths better than gradient boost. So that's not a whole lot better, really. And the training and test accuracy are so close here that I think naive Bayes is underfitting still. So I don't think it would generalize the very best. And also something when you compare all of these, for some reason, when I extrapolated from cross-fold data to the full data set, gradient boost jumped up big time in performance. And I think that might have been because for a lot of my cross-folds, I was actually just testing on a portion of the data. Like just to speed up training times, I would reduce the training set to only like 50% because it was just taking so long to do these tests. So I think gradient boost really helped by just giving it the full training set to test on rather than just a subset. Okay, before we discuss what I recommend to be the best model, I wanted to discuss feature importance as well, because that should play a part. I found through looking at the feature importances, we're not going to get any for k-nearest neighbors. It's not really possible. But for the decision tree models of random forest and gradient boost, we can see that they are using very similar words or some very similar words are being the most influential in these models. And that's most notably word 249, word 78, and word 87. So these must be pretty emotionally charged words that really help distinguish which class the review is in. Furthermore, for naive Bayes, I was able to generate some probabilities by class here. Um, Naive Bayes prioritize different words. We can see here that it was very influenced by word 0 and word 3. But interestingly, word 437 does appear in all three models. So that must be a very telling word for um, these sentiment reviews. Okay, now let's look at some misclassified samples between all the models. So we know from the documentation that a 1 is positive and a 0 is negative. And we see a pretty even distribution of misclassification between the classes, except for K nearest neighbors, which really struggled on the negative reviews here. Um, we can see that it classified almost double negative reviews over positive reviews. And whereas, these three, they had pretty even split of misclassification between negative and positive. I also found that there were 1,400 samples that were misclassified by all four models. So I think if you were to dig into this problem further, you would want to look at those samples to see why they are so difficult for all these models. And I also looked at which samples were misclassified uniquely to each model. And random forest really stands out where it only got 136 samples wrong that none of the other ones did get wrong. The rest that it got wrong, other models also got wrong. So that is something interesting to know and to take into account. Okay, let's conclude this because we're a little bit over time. My apologies. Um, in conclusion, I think the gradient boost algorithm shows the best ability to generalize. And this is mostly because K nearest neighbors struggled. The naive Bayes model, that seems to still be underfit. And the random forest was just slightly outperformed by gradient boost. So some other things to take into account that really help me think that gradient boost is the best solution for this. It doesn't take very long to train. Like once you find those hyperparameters, the model does train pretty quickly. But man, finding those hyperparameters can take a while, especially if you have a lot of N estimators. Um, it's also fairly easy to interpret. We can see from the previous slide that you can pull out these feature importances that show which features are influencing the model the most. And then I also have the hyperparameters, the best hyperparameters displayed here, and its best scores. So yeah, I believe that concludes my homework for. Thank you for listening.